Are you seeing the screen? Just check. Oh, yeah.
Yes, sir.
All right, so we're going to start. So we're going to do some questions from module 1 and from UV-IR gravimetry. In the morning, I'm just going to post the answers to some questions. I'm not going to do a live. So I'm just going to work on the answers. They can look at that. Give me a second. Ready again. All right, so this one is from, all right, so the 2022 paper, it was a lot on acid-base properties. For that reason, and a little on aldehydes and ketones. So not much is going to come back from that. So I'll start with 2021. This is 2017. Or 2021, organic chemistry question that is already on the channel. And 2019, a lot of that was on benzene. It's not here because it is already on the channel. Right? So the 21 organic and the stuff, every question on benzene from about 2010 up, I posted it last night. So I won't be doing any benzene. Right? And nothing to do with acidity and basicity of organic. That came a lot last year. All right, so just to get that out of the way. All right, so state 3 characteristics of a homologous series. All of you should be able to do that. Do it quickly. Members of a homologous series, anybody want to mention any property quickly?
The same functional group.
Same functional group. Anything else?
Each successive member differ by a CH2.
Right, it differs by a CH2 group. They have the same general formula. And they have similar chemical properties. All right, so moving on. So this is 20. On analysis, 1 gram of a compound containing carbon, hydrogen, and oxygen provided 0.4 gram of carbon and 0.5 gram of oxygen. Compound A has a molecular mass of 60. Calculate the empirical. Right, so we have carbon, hydrogen, and oxygen. They give us the mass of carbon and oxygen, so we need the mass of hydrogen. So if you want to do this question, you're going to add up the mass of carbon and oxygen and subtract it from 1 gram. So on analysis, 1 gram of a sample, it would be 1 gram minus 0.4 plus 0.54. 0.94. It should be 0.06. So the mass of hydrogen is 0.06. So if you remember the empirical formula calculation, the first thing you will do is calculate the moles of each. If you remember, mole is mass divided by molar mass. Oxygen 0.54 divided by 16, and hydrogen 0.06 divided by 1. Once you do that, you will compare the three numbers and divide by the smallest one. That's 1 carbon, 2 hydrogen, and 1 oxygen. Empirical formula is CH2O. For the molecular formula, we're going to find N. N is the molar mass of the compound. So compound A has a molecular mass of 60. It's the molar mass divided by the empirical formula mass. The molar mass is 60, and the empirical formula mass, 1 atom of carbon, that is 12, 2 atoms of hydrogen, that is 2, and 1 atom of oxygen, that is 16. 16 and 2, 18, 18 and 12 is 30. Answer there is 2. What you're going to do now, to get the molecular formula, you multiply the empirical formula by whatever you get for N. You times it by 2, and you will get C2H4O2. And so that is the molecular formula, and this is how you work out this question. All right, so you can just take a screenshot and we'll continue. This is write the general formula of the homologous series to which A belongs. It was C2H4O2. Once it has 2 oxygen, that means it's more than likely a carboxylic acid. So let us draw the structure and see if we get a carboxylic acid. It was C2H4O2. It wouldn't be a carboxylic acid. The general formula. C2H4O2. All right, this is not any actual functional group. All right, so based on this, when you have 2 carbons, we should have 4 hydrogen. So we could say CnH2n
Plus 1.
No, it would be O2, or I said CnH2nO2, as in they are just O. Well, N is the amount of carbons, and when you have the N, you generally use it to get the amount of hydrogen. So the amount of carbon is twice the amount of hydrogen. But based on this, it's just random. It's not like a regular, let's say, alkene or alkene. In terms of how the O2 drops in, it don't follow the amount of carbons. The hydrogen, that would be H2N, based on what we see here. For me, I will just include plus O2. I will double check this, and if there's any correction, I will let you know. I will, but for now, this is what I would work with. Because if you check, there's no functional group with with 2 carbons, 4 hydrogen, and 2 oxygen. Because carbon has to have 4 bonds. But based on this, that is what I will put. Carboxylic acid. Look at that. I was correct. It is. All right, so if it's carboxylic acid, then it's CnH2n plus 1, a functional group.
Yeah, that is why I see the plus one here.
That's right. I was checking the hydrogens incorrectly. I didn't see that it will actually match up to the 4 hydrogens. So join it out, it's carboxylic. All right. Oh, and they say now draw the structure. Draw the structural formula of the chloro substituted compound of A. This is a carboxylic acid, and they're asking for the chloro substituted compound of A. Well, we know that carboxylic acid, if you react with certain compound like SOCl2, you could get an acid chloride, an acyl chloride. You could replace the OH group with a chlorine group to get the acyl chloride. This is the structural form of the chloro substituted compound of A. So if you have carboxylic acid, SOCl2, you can get an acyl chloride. Right, as I said, we won't be looking at any with acid base characteristic. All right, so here we have primary alcohol. What type of alcohol is this?
Secondary.
Is it repeat?
Secondary alcohol.
And how you know it's secondary alcohol?
Because
it was only binding to 2 alkyl groups.
All right. Let's just do a quick displayed formula. We start with a carbon, then a next carbon with a hydrogen, OH, and then a next CH3 group. Right. So it is secondary. So you can use 2 things to know if it is secondary: the amount of carbons or the amount of hydrogen. 1 hydrogen, it is secondary. And as the person said earlier, there are 2 carbons directly attached to this carbon with the OH group. So you are correct. This is secondary and this is primary. So if you want to distinguish between primary and secondary alcohol, which reagent should we use?
The iodoform test.
Right,
Sodium and iodine.
right. So you just need, so you must remember your reagents. Right. For this reaction, we need iodine and sodium hydroxide. Even though they did not ask you, let me just scroll and see if they asked for observation. No, they did not. But let us say they had asked for observation. What would you expect to happen to this alcohol? I'm going to call it, well, it's propanol. So what would you expect to see? What would you expect a color change for propanol?
No, sir.
Right, because the iodoform test does not, the primary alcohols, excepting for ethanol, will not perform the iodoform test. The secondary alcohols and keto and the carbonyl group will do the iodoform test. The iodoform test is for secondary alcohol and the carbonyl group. What would be the observation with the secondary alcohol?
So yellow precipitate.
Right. And again, what is that yellow precipitate called?
Triiodometer.
Right. So that asks you for observation, you will get a yellow precipitate of triiodomethane. All right. Next, which compound is this?
Benzene.
Okay. So we have benzene and we have an alkene. As we know, benzene, even though both of them have double bonds, benzene does not react like an alkene. So which reagent can we use to distinguish between benzene and the alkene?
Liquid bromine.
All right, we could use bromine. Whether liquid or aqueous, doesn't matter.
Liquid. Okay.
So you could use the liquid, you could use aqueous bromine. Any reaction of alkene, KMnO4, right? Because as we said, benzene does not react like an alkene. For it to react with bromine, what is needed? What is needed if it should react with bromine, the benzene? Which catalyst is needed? FeBr3. Right? So remember, benzene will not react with bromine unless you have the catalyst. You can just choose any reaction that can give you a visible color change. Don't just choose any reaction. You must be able to observe. Right? So you would have your two liquids in a test tube or a beaker, and you add your bromine or your potassium permanganate, and you observe. Right? So just a simple description of what you would do. Right? And that would be it. So that was an easy 15 marks. With all of 30. All right, so let us just look at which year is this. I think it's still 2017. All right, so define the terms primary, secondary, and tertiary alcohol. Give relevant examples using structural formula. So how would you define primary in terms of alcohol?
primary alcohol could be defined as when the functional group, and you put the OH in brackets. So let's say the functional group is directly attached to one carbon or one specific group alone.
So the carbon atom bearing the OH group, or if you want to say the carbon atom to which the OH group is attached, carbon atom bearing the OH group is bonded only one carbon atom. And they want an example. As you can see here, the carbon atom bearing the OH group is bonded to only one carbon atom. And then for secondary, we would say this same thing, except we change it to two carbon atoms. All right, look at the gist now, is bonded to two carbon atoms. And then for tertiary, you would write this same statement and put bonded to three carbon atoms. An example of the tertiary now. So the carbon atom bearing the OH group is bonded to three other carbon atoms. And this one now will take some reading. Just a second. All right, so two isomeric phenyl alcohols, A and B, C8H10O, C8H10O. Isomeric phenyl alcohols, A and B, and treatment with concentrated sulfuric acid, compound D. They treat phenol or phenyl alcohol with concentrated sulfuric acid. Well, let me not put phenol. We treat an alcohol with sulfuric acid and it produces compound B. Compound B decolorized bromine bromine water. Right? So compound D, decolorize bromine. Then now, oxidation of the isomers with acidified potassium permanganate produce compound E and F. When you oxidize the alcohol, you get compound E and F, which both gave a yellow precipitate with 2,4-DNP. Right, so both E and F reacts with Brady's reagent. However, on the compound F formed a silver mirror with a solution of silver nitrate. So both E and F reacts with Brady's reagent, but compound F reacted with Allen's reagent. All right, so that was the information given. You have the two isomeric alcohols treated with sulfuric acid, you get compound D. That's a separate reaction. It is not linked to what is happening over here. First question, before we look at the actual questions, when you treat an alcohol with sulfuric acid, what are you doing to the alcohol?
You're
Any idea?
dehydrating it, so you get an alkene.
Right. And we know that alkenes will decolorize bromine water. Right, so that is good. Question, when you react alcohol with potassium permanganate, what are you doing? Alcohol.
It's getting oxidized.
All right. And when you oxidize an alcohol, what are the possible products?
For primary alcohols, it's an aldehyde. For secondary, it's a ketone.
All right. Now, once you see Brady's reagent, which functional group can react with Brady's reagent?
Both aldehydes and ketones.
All right. But which one will only react with Tallen's
Aldehyde.
reagent?
Aldehyde.
All right. So compound F is compound F and aldehyde are ketone.
The aldehyde.
That is correct because it reacted with Tallen's. Now remember the question started out by saying you have two isomeric alcohols. And by now you should be realizing that one of those alcohol is primary and one of those isomeric alcohol is secondary. So whichever alcohol produces compound F, it should be primary. And whichever one produces compound E, it should be secondary. And because we can safely say that compound E is a ketone. All right, so let's go now and actually answer the questions. It says, state the type of reaction which produce compound E and write its structural formula. So what is the type of reaction that produce compound D? You already said it, it is dehydration. So that is why knowing your reagent is important, because once you see sulfuric acid reacting with alcohol, you should know it is dehydration. Draw the structural formula of compound D. All right, before we draw D, we need to draw compound. We need to draw the alcohol. They say it's a phenyl alcohol. The formula C8, it has 8 carbons. But we know that the benzene ring has 6 carbons. right? So that is the benzene ring, which means that two carbons must be attached to the benzene ring. You can start with a secondary alcohol or a primary alcohol, doesn't matter. So this would be one of the isomers. You can check the molecular formula as well. Instead of the skeletal structure, just quickly draw the carbons. One, on the OH, H, CH3. You would have a H here, one there, one here, and one here. 6 carbons on the ring plus 2 more, that's 8. 1, 2, 3, 4, 5, 6, 7, and 3, that's 10 hydrogen. And 1 oxygen here. Right? So that is the structure of the one isomer of the phenyl alcohol. All right, so if you dehydrate this alcohol, you just put a double bond there. Do not write back CH3, alkene, so it is CH. All right, so this is how you would get compound D. So you are dehydrating this compound. Remember, H, H, H. You are taking off the OH group from this carbon and the hydrogen from this carbon. And so you get the double bond. That is correct. And I'm referring to I'm referring to Bless TV in the comment section. All right, so that's compound D. Let us scroll down now. All right, so it says explain the reaction which led to the production of E and F. So jettings, and so we know that when alcohol react with potassium dichromate, that process is oxidation. All right, so alcohol with potassium dichromate, it is oxidation. All right. Also, we know that primary alcohol will be oxidized to an aldehyde, and secondary alcohols are oxidized to ketone. So the reaction that led to E and F, so E was which one? F was the aldehyde, right? So the reaction that led to the formation of F is the oxidation of a primary alcohol, and the one that led to the formation of E is the oxidation of a secondary alcohol. So we know that E was the ketone, so that had to be the oxidation of a secondary alcohol. All right, so I'm going to scroll again. All right, so now they're asking us to deduce the structure of E and F. So we said that F was the aldehyde and E is the ketone. All right, so if this would have been the secondary alcohol, which would have produced ketone, which is compound E. So for compound E, you just convert this into a ketone. All right, there you have your ketone. And then now for the aldehyde, you know that the double bond would have to be at end. So this would be compound E. And then compound F would be the aldehyde. And they're asking for compound A and B. Compound A would give you the ketone. Let me just check if it, just check up. Two isomeric alcohols A and B. Well, it doesn't matter. All right. We just need to draw a primary and a secondary alcohol. So this is compound F. The compound F would come from primary alcohol. For the OH would be on the carbon at the end. As we already said, OH would be here. So these are compound A and compound B. This question required a lot of analysis. And someone asked me a question, let me check. Right, sir, could you do it over once more? Which part exactly? As in how we get E and F? Which part? Because I'm just seeing your message. Let me know quickly. Model trees in the morning. The person asking. And yes, it is the benzene ring that makes it aromatic. All right, so let me just run back the question again very quickly. So you have two alcohols, A and B, two isomeric alcohols, right? Something is different about them. Not just isomeric alcohols, phenyl. So once you hear phenyl, you know it as a benzene ring. And the benzene ring has 6 carbons already. So if the alcohol has 8 carbons, that means these other 2 are attached to the ring. All right. So when they say phenyl alcohol, it is not phenol. All right. Next thing it says on treatment with concentrated sulfuric acid. So we know we have an alcohol, that's for sure, right? On treatment with sulfuric acid, you get compound B. Once you react the alcohol with compound with sulfuric acid, you know you are dehydrating the alcohol. So the reaction is not taking place on the benzene ring. It is actually taking place at the carbons attached to the ring. So compound D, you remove the OH group, convert it to an alkene because you are dehydrating it. So this is compound B, right? And we'll finish with that. Next set of reaction now. Oxidation of the isomers with acidified potassium dichromate produce compounds E and F, right? You cannot know this structure of the alcohol as yet until you read all of the statement. When you oxidize the alcohol, you get E and F, which gave yellow precipitates of 2,4-DNPH, which gave yellow precipitate with this. You know that E and F at this point is both aldehyde and, well, can be aldehyde or ketone. Right? So once it reacts with DNP, it can be aldehyde or ketone. The follow-up now says compound F formed a silver mirror with a solution of silver nitrate. Only compound F react with the silver nitrate to give the silver mirror test. So at this point, you know that compound F is an aldehyde and compound E is a ketone. All right? Now, if F is an aldehyde and E is a ketone, your isomeric alcohols are primary and secondary. So that is how I know that one of the alcohol must be primary and one has to be secondary, because I got aldehyde and ketone. Right? So that, and if it is a secondary alcohol, my OH group here. OH cannot be on the ring because remember, benzene don't react like regular compounds. The OH group is right here, convert it to an alkene, you oxidize it, convert it to your aldehyde and ketone. All right. So you would have to make it secondary to get the ketone. And the primary alcohol would have been here, that would have been converted to the aldehyde. Right? So that is how I was able to analyze the question. All right. Hopefully that cleared it up for you. All right, then the next part now. It says comment on the reaction of A and B to plain polarized light. Once you see plain polarized light, do you know what it is referring to? Or why it is asking you that? All right, so once you see plain polarized light, it is referring to chiral. Yeah, go ahead.
Oh, no. I just was going to ask what UV, but never mind.
Okay. Plain polarized light, it is referring to optical isomers. Remember, optical isomers rotate the plane of polarized light. Optical isomers, they must have a chiral carbon, or we say a chiral center. And we know that a chiral carbon is a carbon with 4 different groups attached. Comment on the reaction of A and B to plane polarized light. So we need to now look and see if either A or B is an optical isomer. Then we can know what to say, if it will rotate it or not. Let us quickly draw back the structure. We can start with the secondary alcohol. All right. Does this compound look like it has any chiral carbon? All right, so let's check. And let me remind you, when you're looking for a chiral carbon, you're not looking for an atom that is directly attached to the carbon, all right? So if I am assessing if this is a chiral carbon, everything on this side is a group, all right? So the C alone is not the group. Everything to the left of it is a group. Everything to the right, everything to the left, right? Whatever is over here, whatever is above, whatever is below, circle. That is how you determine the chiral carbon. So this carbon here has an OH group above, has a hydrogen below, has a CH3 group to the right, and it has the benzene ring to the left. Is it chiral?
Yes, sir.
Right. So if we had called this compound A, then we would say A will rotate plane polarized light. Did not ask for any explanation, it just a comment on the reaction, right? So A will rotate plane polarized light. All right, draw B quickly. Do you think B has any chiral carbon? Right? If I should check this carbon, right? It has an OH group above, all of this to the left, a hydrogen to the right, and a hydrogen below. Is it chiral?
No, sir,
Can you tell me why?
because you have two hydrogen, which is the same functional group.
That is correct. So call this one B. So say B will not rotate. B will not rotate the plane of polarized light. Right, so that is all you know. So the polarized light, it was hinting whether or not it is a chiral compound. All right, so let's want to scroll again. Don't have any space to work this one. All right, but, all right, so this one now it says explain. Let me see if the ear is on it. All 2014. All right. 2016, I think those were benzene as well. So probably that's the reason. And for 2016, number one, it had to do with some combustion analysis. It is on the channel, so didn't do it here. All right, so compound A, that's part B, explains the terms primary, secondary, and tertiary as it applies to haloalkanes. The same thing we did for alcohols is the same thing you will do for primary haloalkane, just like we said for the primary alcohol. The primary haloalkane, the carbon atom bearing, you don't have to put bearing, if you want to say, all right, let me put bonded. The carbon atom bonded of the halogen is bonded only one carbon atom. Right? So the carbon atom bonded to the halogen is bonded to only one carbon atom. So for example, this carbon is bonded to chlorine. It is only bonded to one other carbon atom. If it was a secondary haloalkane, put it over here, it would be bonded to two carbon atoms. So this is a secondary haloalkane because it is the carbon bonded to the halogen, in this case chlorine, it is bonded to two other carbon atoms. And for it to be tertiary, it would need to be bonded to three carbon atoms. Right, so this one over here is primary, this one is secondary, and this one down here is tertiary. So that is how we would explain them, explain the term. All right, so let's continue. All right, so compound A is one of two straight chain bromoalkanes, which can exist in two isomeric forms having a molar mass of 137. Bromine has a mass of, well, it is isotopes, it's 79 and 81. So you would subtract, try this 79 first, and whatever remains is the hydrocarbon portion. Subtract 79 from 137, and whatever mass remains, that should be attributed to carbon and hydrogen. All right. But I did not work it out ahead of time, ahead of this session. I'm just going to, let us say it's 4, 12, 4 is 48. I think it's about 4 carbons that would be in it, right? So write the name of compound A, all right, assuming it's 4 carbons. Remember now, it's a straight chain, so we're not branching it. So if it's a straight chain, and it is also an isomer, what type of isomer would it be? We have our bromoalkane that is a straight chain. What type of isomer?
Structural.
Please repeat.
Structural.
Right, but you have 3 types, right? Chain, positional, and functional group.
Positional.
Right, has to be positional. So this would be bromobutane. And then part 2, explain the nature of the isomerism exhibited by compound A. They're basically explaining positional isomerism. You would mention that it is exhibiting positional isomerism. The reason for that, right? Both of them are straight chain, right? So the only thing that will change is the position of the bromine atom. Since both isomers are straight chain, the only thing that will be different is the position of the bromine group. That's the only thing that can be different. You can put 1 on carbon 1, and then in the next one, you put it on carbon. You can have 2 bromobutane, and you can have 1 bromobutane.
Sir,
Yes.
for the mass of bromine, wouldn't it be 80 like how it's 79.9? Because I try working it out with the 4 carbons and
you
get
average.
136.
It work with 80?
I tried working it with 79 and I got 136 instead of 137, but the mass number of it would be 79.9. So I'm asking if we wouldn't just round off.
Yes, 80, yeah. It was 79.9 tons. Right, but how much carbon it work with? The 4 carbons work?
Yes, sir, 4 carbons.
Right, so bromobutane. And then now, part 3, draw the structural formula of the isomers. That is what we just did. So down here, you would draw the 2 bromobutane and the 1 bromobutane for 2 more marks. All right. And another bromoalkane B, the same molar mass, when refluxed with aqueous sodium hydroxide, produces an organic compound C and an aqueous solution of B. It was found that the rate of the reaction is determined by the concentration of B. Take the name of compound B. Let's go again. To the screen. Another bromoalkane B with the same molar mass, when reflux with sodium hydroxide produces, it was found that okay. Does anybody, before I answer it, do you have any idea? All right, let me show you where the hint is. It was found that the rate of the reaction is determined by the concentration of only B. So it's an haloalkane. So the reaction mechanism is SN1 and SN2. Remember, SN2 is bimolecular, meaning both the nucleophile and the haloalkane affects the rate of reaction. But SN1 is unimolecular, meaning only the haloalkane will affect the rate of reaction. All right? So this is what you should use to know the name of the compound. So if you weren't paying attention to this, I don't know how you would have gotten the actual name of the compound. The next thing I'm going to ask, now that you know that it is, the mechanism is SN1, what does that tell you about the structure of the compound? It doesn't know it's now SN1.
So tertiary haloalkane.
All right, it can be tertiary or secondary, yes. Good. So if it's tertiary, if you want to make it tertiary, remember now they say that it is the same molar mass, which means that you have how many carbons,
4.
right? So we are going to set it now so that it becomes either secondary or tertiary. Let's make it tertiary. We have 4 carbons. Let's see if we can make it tertiary. So CH3, H3, E3H, and then Br above. And so that is, all right, so what would be the name now of this compound that I just draw?
2-methyl. No, 2-bromo, 2-methyl propane.
2-bromo, 2-methyl. Right? That is correct. Before I run through the mechanism, describe the reaction between a solution of B and aqueous silver nitrate. And so if you remember in this reaction, right, you have the bromoalkane. But if you remember how the mechanism goes, the bromide ion will be displaced, right? So it will be, well, not really displaced, but it will come off. So it will be in solution. So if you add silver nitrate solution, the silver ion can react with the bromide ion to give silver bromide. Remember from qualitative analysis, right? So silver bromide describe the, right, so the reaction is that the bromide ion that was displaced from the haloalkane can react with the silver ion to give you a precipitate of silver bromide. So that is what would happen. All right, so I'm just going to scroll up to a blank page and do the mechanism quickly. All right, there are joins. I'm checking if I have any blank page. I think this page is good enough. So let's do the mechanism here. All right, so we know it's SN1. So what will happen in the first step? What major event occurs?
The formation of the carbocation.
Carbocation.
What type of bond breaking occurs here?
Electrolytic.
Right? Once the bond is polar, heterolytic breaking occurs. And you will get your carbocation. This is the rate determining step as well. That is why it is unimolecular. The rate is dependent on the Haloalkane. And then what is step 2? What will happen in step 2?
Nucleophilic attack on the carbocation.
Right. What is the nucleophile?
Bromine.
Mm-mm.
Bromide ion.
Mm-mm. There's,
Water.
it could be water if it was hydrolysis, but
No,
for
the
K,
hydroxide.
right. So it's a solution of sodium hydroxide, right? But remember, when you have a solution, the ions are not together. So in this solution, in terms of an equation, you will see sodium hydroxide, right? But in terms of the mechanism, the sodium ion is separated from the hydroxide ion. So the hydroxide ion is your nucleophile. So nucleophilic attack on the carbocation. Just remember, if this mechanism should come, this is not your nucleophile. All right, so let's continue. Why am I using curved arrows and not fishhook?
Because the two electrons are going, not one.
Right? We only use fishhooks if you are transferring a single electron. Right? So at this point, we will get our alcohol. And what type of alcohol is this?
Primary.
Tertiary.
Right? So remember, the carbon with the OH is attached to 3 other carbons. So it is tertiary. All right, for the person in the comment section about 2020, for the 2021, that's already on the channel. So not all of it, the question, the organic chemistry question from 2021, it's already worked on the channel. 2022, organic chemistry, it was heavily based on a little on polymers, then acidity and basicity of organic compounds. So I'm not going over that because you're not seeing it back this year. The part with aldehyde and ketones, I didn't remember to cut that part. I'm going to work the answer and upload it in the morning. So yes, I post 2 videos on the channel. One with the reaction mechanisms for different past papers. You just need to look at that one. I did not do any benzene tonight because I posted a video yesterday with benzene questions, right, from about 2010. And the last time benzene came was 2019. I worked it up to 2019. And if you watch the video, you realize the questions on benzene tend to repeat. All right, so I did not work it because it's already on the channel. All right, and I think that benzene is coming tomorrow, so just ensure you know your reagents and how to do the mechanism.
So it's only one mechanism for benzene, right?
As in, well, it's electrophilic addition, but you have nitration and halogenation.
No, like for the mechanism.
Oh, no, yeah, it's just one mechanism.
Okay.
Yeah, but it's one specific type, but you need to know halogenation and nitration. But in terms of how it happens, it's similar. That's what I mean.
It would have just be the one when you add the nitrogen ion to the benzene ring.
No,
That
there's a next one. There's the one with halogen, Br2, halogenation. So you need to know the mechanism for nitration as well as halogenation.
Okay, sir.
Yeah. Benzene hasn't come since, I'm just replying to someone in the comment. Benzene hasn't come since 2019. More than enough time now for it to come back. Yeah. 2019, 4 years. And benzene is a major part of our organic chem. All right, so I'm going to stop it here from module 1. We're going to do some module 2. I need to, all right, give me a second. All right, I'm just going to, this is not a past paper, but I'm just going to spend like 10 minutes and just go back through the need to know, all right? Just in case it comes. These ratings are fine. All right, question. When it comes to ROSA, right, with the boiling point composition curve, what are the two deviations that you can get? Anybody remember the two types of deviation?
Standard,
Positive and negative deviation. If you need to draw it, just remember you draw a straight line, which this line represents an ideal mixture. All right, that is an ideal mixture. And you, for this mixture, you will have, if you were to boil it right, like this curve. You will have your vapor composition and your liquid composition. Before we get to this, to explain the fractional distillation, a straight line is the ideal mixture. If you're asked to show negative deviation, it goes above the line. Sorry, this is boiling point. So negative deviation, the boiling point will be higher. Sorry. I mix up myself. So for boiling point, negative deviation is above the line. So this is not explanation, it's just to basically give you something to memorize in case they ask. If it's the first time you're seeing this, I don't understand it. All right. When it comes to boiling point composition curve, ideal is the straight line. The one that curves upwards is negative deviation. This one is positive deviation. So these are for the boiling point. Negative above it, positive below it. If it's vapor composition, it's the opposite. Right? So these two if you get a vapor pressure graph and you want to show positive or negative deviation, it will be the opposite. So for negative deviation, it would be below the line. And for positive deviation, it would be above the line of the vapor pressure. Just do that quickly. I'm just putting VP for vapor pressure. This is negative deviation. And this is positive deviation. That is when on the y-axis is vapor pressure. So over here is boiling point, over here is these two are for vapor pressure. Just remember that. All right, so I'm going to clear the screen. Quickly, what is this graph showing? Or what type of mixture is this?
Azeotropic,
Right. How you know it's azeotropic?
because
The overlap.
Right. This is what you should normally see. All right. I'm just going to call this normal mixture. If you should get a curve, once the two lines meet somewhere in the middle, let me not say middle, somewhere in between these two lines is azeotropic. All right. Once they meet like this, it is azeotropic. Last thing. If you're asked to explain the principle of fractional distillation, I'm going to use the water and ethanol. Right? So if once you see the graph, if they give you a graph already, or let's say you don't get a graph and you have to draw it, once you draw it like this, right? This point here is for water. Reason why it is for the, say, of water boils at 100, ethanol boils at 78. Good. So the higher boiling liquid, that is what you're starting with. How you will number it? Let's say we typically use 0 to 1. All right. What you're trying to get is the, so this is fractional distillation. Right? You're trying to get 100% of the more volatile liquid. All right. So the 0 here means that you have 0 ethanol. Good. So you have a mixture basically that is just water only. When you get to this end, you just have ethanol only. So anywhere on this line is a mixture of alcohol and water. But at the very start is just water. And at the very end, you would have completely separated the mixture and have only alcohol. Remember now, this top line is the vapor phase. The bottom line is the liquid phase, or the liquid mixture. All right. So this is the mixture in the liquid state. Up here is after you pour the mixture. Let me just draw a line. So let us say you start in the mixture here. You will have a mixture of this composition, right? At this point, if this is one alcohol, 1 mole, right? So is mole fraction. So the 0, this is 1, which means that this is about 0.2. So if you boil the mixture with 0.2 alcohol, draw a line going across the vapor phase. Need it to be a little more narrow. All right, so you draw a line across. This is the vapor. So this here, you boil the liquid, it becomes a vapor. Then you allow it to condense. When you allow it to condense, it will have a new composition. So this is 1, so here is about, let's say, 0.7. The other mixture with 0.2 alcohol, right, which would mean it has 0.8 water in it. When you boil it and condense it, the new mixture has 0.7 alcohol. If you should boil this mixture again, you boil it again, it will have a new composition. All right, so this line at the top, it is showing the composition of the vapor. So what it is saying, the vapor is richer in the more volatile substance. All right, you condense it, you boil it again, the vapor is even richer in the more volatile substance. And if you boil this part again, then you can see that you will get 100%. And you will label it. So let's call this part A. All right. So when you boil A, it will have, let me call this part B. I could call this C. So these are the different composition of the vapor. Well, this will not be a vapor composition. This will be it. When you boil the mixture of A will have a composition of, right, let me put A1. So this is the liquid with vapor composition A1. And when you condense it now, this is liquid B, and then it will have a vapor composition B1. And if you condense it, that's liquid C, and when you boil it again, it will have a vapor C1. All right. So from A to B to C, your vapor is getting richer and richer in alcohol until you just have alcohol only. So that is how you would explain fractional distillation. You don't just do it one time. You have to do it several times in order to obtain a pure liquid.
And sorry, if they give us a graph to read, we start where the 0 mark is, right?
All right, so if they give you a graph to read, it will not start at 0. So it will be something just like this on the board, where it will start at, say, A. So Remember, remember if you start at 0, like here, that is not a mixture. It is just one of the liquids. So they will start somewhere along the line. Because it has to be a mixture. All right, I remember last thing. For the azeotropic mixture, let us say, all right, let me do this. So this is again ethanol and water, right? So based on the let's ask you, use this diagram to tell why you cannot get 100% ethanol. What would you say? Well, don't answer as yet. Starting here. We start with this line here. All right, so we're starting with that all right, I'm going to call it A. If you start distilling a mixture of ethanol and water, can you get 100% ethanol? Explain.
No, sir.
First,
No,
it's
sir.
an azeotrope.
Right, because once it reaches about this, so this point, it's about, let's say 95%, right? So once you get 95% ethanol, the mixture becomes what?
Azeotropic.
Right. So at 95% ethanol, it becomes an azeotrope. And if it becomes an azeotrope, what does that mean?
It has a stable boiling point.
Right. So the mixture at that point, boiling the mixture again will not separate it. So all along, when you were boiling the mixture, as you see over here, you are getting more and more of the alcohol. But this one, once you reach the azeotropic point, you cannot pass it, which means that in order to get 100% ethanol, or not just ethanol, if they give you an azeotropic graph, right? If you want to get 100% of it, you will have to start with a mixture that has passed the azeotropic point. Is that clear? So if they give you a graph that is an azeotrope and ask you how you can get 100%, you have to start with a mixture above the azeotropic point. Is that clear?
Yes, sir.
Right. Yes, so these are the types of graph that you will have. Right, so I'm going to pull up there's not any on roads line this set. I will upload one in the morning, but I just wanted to explain the graphs. This is phase separation, specifically Rhodes law. So for Rhodes law, you should be able to draw you should be able to do these.
Sir,
Yeah,
sir, you have any question on steam distillation, the calculation part that you could probably work?
not terminal. I'm going to post that in the morning. So as I said, I'm not going to do a live session. I'm just going to work question and post it.
Sir, I have an exam tomorrow morning.
No, once you finish, you just check it. You have my number, so You can put some. All right. Look the next set. All right, so let's continue quickly. I'm a bit tired. All right. What is accuracy?
Accuracy is how close the measured value is to the true value or the accepted value.
Right. And so what I'm going to do in the morning, I'm just going to write the answers and post it. All right. So in terms of these, the writing parts. Right. Accuracy is how close the measured a measurement is to the true or accepted value. And what is it for precision?
Precision is how the measurements are close to each other.
That is correct. And in terms of a standard solution now, right, sodium carbonate is sometimes used as a primary standard, yet its molecular mass is only 84. There's three reasons why sodium carbonate is used as a primary standard. So tell me something about primary standard.
Primary standard must be stable in the air. It must have a high relative molecular mass. It must be soluble in water and form a standard solute. Yeah, it must be soluble in water. It is non-hygroscopic, meaning that it does not absorb moisture.
Wonderful. And so when you get to this part, it's one reason why sodium hydroxide may not be used as a primary standard. That part, it absorbs moisture. Remember, even in combustion analysis, we use it to absorb CO2, right? It can absorb moisture. I don't have to put that. Any of the reasons why sodium carbonate is a good primary standard, you can list it now that sodium hydroxide does not have any of those properties. It would not be able to be obtained in high purity, not stable in air. You can just, whatever you put up here, just write back one of them down here. All right, so a student, by the way, this is 2021. As I said, the organic question for 2021, it was previously worked and uploaded on the channel. All right, so a student standardized a solution of sulfuric acid using sodium hydrogen carbonate as the primary standard and found the concentration of the acid to be 5 moles per bm cube. All right, so sodium hydrogen carbonate. When any form of equation that you're going to write, put state symbols, or else you will lose marks. All right, so sodium hydroxide plus sulfuric acid, sodium hydrogen carbonate. I check it's sodium sulfate plus carbon dioxide plus water. You're going to need a 2 in front of sodium carbonate, and you will need a 2 in front of water. Right, then it says the mass in grams of the sodium hydrogen carbonate. Calculate the mass in grams of the sodium hydrogen carbonate that the student neutralize the acid if 23.5 cm³ of the acid were used from the burette. Right. This is what you will do. So to get the mass, so we know that mass is equal to mole times molar mass. But you don't have the mole of sodium carbonate. What you have to do is to find the mole of sulfuric acid, because you have the concentration of sulfuric acid and you have the volume of sulfuric acid. You multiply the two of them, you will get the number of moles. It's unlikely to come, but I'm just working it. All right, so the mole of H2SO4 is equal to 0.5 converted the cm³ into dm³. Yes, I think benzene is coming. It's been a long time. So the answer for that, I have already. All right, so once you have concentration and volume, you multiply the two of them, you will get the mole. Now, what you really want is the mole of sodium carbonate. You have to use mole ratio. So it's 2 mole of sodium carbonate to 1 mole of sulfuric acid. The mole of sodium hydrogen carbonate is 0.1175 times 2, and you get 0.235 mole. Once you get the mole, you can go ahead now and calculate the mass. Mass is mole times molar mass. So 0.235 times 84, you will get 19.74 grams. Right? So that is how you would get the mass. If I had to guess from module 2, IR, UV, gravimetry. Give me a second to plug in my laptop. Let's see how much it is. 39 is enough. All right, let's continue. All right, so we're going to go to standard deviation calculation. after conducting a titration, a student at the following titer values. Now remember in a titration, you are going to use the closest values. All right, so this cannot work, this can't work, this can't work. All right, titration, these values are not close. So these are the three values that you would use to calculate the, no, it's gravimetry. Please tell me no that. All right. So the question says, determine the mean volume from the titer values to be used in the calculation. So the mean volume is the average volume, basically. And to get that, you would say 22, 25.25 plus 25.35 plus 25.30 divided by 3, and you should get 25.3. So that is the average volume. All right, using the following equation, justify the choice of the titer values selected. Basically, no. Basically, they're asking us to calculate the standard deviation. To calculate the standard deviation, the formula is there. So it is square root the sum of x minus x bar squared divided by n minus 1. All right, x are the individual measurements. X bar is the mean, and n would be the number of measurement. I'm going to put trials, right? So the mean was 25.30. So I am going to take away the 3 readings that we used on the table. That would be 25.25, take away 25.30, and we square it. All right, so this is what x minus x bar squared looks like. The answer is 0.0025. We're going to do it again for the next reading, 25.35. You're going to get 0.0025. We do it for the next reading. Now, outside of a titration, we are doing standard deviation, you will use all the values in the table. All right. Outside of a titration, you are going to use all the values in the table. We are selecting values just because it is titration. All right, so we have worked out x minus x bar for the 3 values that we used. Remember now, it must be the sum of x minus x bar. We are going to add them up now. All right, so step 1, work out x minus x bar for all of the data points. Then you are going to work out the sum. So 0.0025 plus 0.0025. Remember, we already square it, plus 0.005. N is the amount of trials. N is equal to 3 minus 1 because we used 1, 2, 3 data points. N is 2. So once you do that now, you're going to take the square root it is now square root 0.005 divided by 2. Final answer is 0.05. So they say use the following equation to justify the choice. So this is your standard deviation. It is extremely small, 0.05. It means that your readings were precise, very close to each other. And remember, we said in a titration, we use values that are very close. So if the standard deviation was say 1 or 1.5, those numbers, it would be high. All right. Even 0.5 is high. All right. Yeah. So the fact that it is 0.05, that is a very small value, which means that the readings that we used are very precise. And so that is that. All right, so here's a gravimetry question. All right, so this type is, so remember you have precipitation and you have volatilization. All right, so this one is volatilization when you're trying to find out the water of crystallization. All right, so 2 gram of hydrated barium chloride. If it's hydrated, it has in water of crystallization. So if you heat the hydrated salt, you're going to remove the water from it, and then it will become anhydrous. Right? The anhydrous barium chloride is after you have heated it. It is now 0.522 grams. In this calculation, the first thing we want to find is the mass of water that was given off. They already give you the mass of the anhydrous barium chloride. In this calculation, we use the mass of anhydrous barium chloride and the mass of water that was lost. To get the mass of water that was lost, you subtract anhydrous from the hydrated. And you should get 0.09. Alright, so you have the mass of water, you have the mass of anhydrous barium chloride. What we're going to do now is similar to empirical formula. Barium chloride and water. We're going to work out the moles of barium chloride and water. Remember, you are using the anhydrous one. So 0.522 divided by, where is it? 1 second, 208 and 0.09 divided by 18. And this is, no, 0.0025. This is 0.005. When if you get the calculation of this, the moles of this of the salt must be smaller than water. If not, you're doing something incorrect. This is 1 and this is 2. So the formula is BaCl2 full stop 2H2O. We have 2 moles of water in the salt. All right, and that is how you would do it. All right, this is our precipitation one. I did not remember to add it to this. I'm just going to work it in this empty section. It's from 2018. So we have a sample of KCl. And the mass of the sample is 0.45 grams. We react it with excess silver nitrate, the precipitate of silver chloride, the mass of 0.8402. So remember, in precipitation gravimetry, right? So let's say you have your solution of KCl, you're going to add a precipitating reagent. In this case, the silver nitrate. Precipitating reagent is so that you can get a precipitate. All right. So you mix, you filter, you wash, and dry, then you weigh. You add your precipitating reagent to this solution, you will get a precipitate. You filter, you wash the residue, allow it to dry, and then you weigh it. That is the procedure for precipitation gravimetry. In terms of the calculation, the first thing you will work out is the mole of the precipitate. Work out the mole of your precipitate. So the mass of the precipitate is 0.8402. And the precipitate is silver chloride. Silver, it should be 143.5. And so, how much that is? .0059. So step 1, work out the moles of precipitate. Step 2, your equation. So in this case, it is KCl with silver nitrate I'm going to get silver chloride and potassium nitrate. 1-to-1 mole ratio between silver nitrate and potassium nitrate, sorry. So 3, you want the mole ratio between your precipitate and the analyte. The analyte is whichever compound or ion that you are analyzing. In this case, you want the mole ratio between KCl and the precipitate of silver chloride. So it is 1-to-1, which means that the mole of KCl is 0.0059. Once you work out the mole of it, you're going to work out the mass of KCl. So the molar mass of KCl is 74.5. Zero point 0.44 grams. All right, now the percentage is the mass of the compound that you calculate. So 0 mass of the compound over mass of the sample times 100. Whenever you want the percentage, so the question had asked you for the percentage purity of KCl. So it was an impure sample of KCl, and they wanted the percentage purity. So for percentage, it is the mass of the compound they calculate over the mass of the sample times 100. 98%. So this is an example of precipitation gravimetry. They don't have to ask you for the percentage purity. You could be asked to calculate concentration. If you are asked to calculate concentration, then they would have given you a volume. All right? So instead of giving you the mass of the sample, they could have said a 25 milliliter solution and asked. In that instance, once you have the mole, you would put it over the volume. No, I'm not going to go over bulk titration, but there are videos on the channel about titration. All right, so that is it for precipitation and gravimetry. This is a regular for this step. So to determine the ethanoic acid content of a particular brand of vinegar, a sample of the vinegar was titrated. So they're asking you for a titration. All right, so as I said, I will post the answers to this. I'm going to write these answers out and post it. All right. So all those definitions, I'm going to just write it and post it. All right. This table here. All right, so this was, I think, which year? We're still on 2019. All right. So using the formula from B1 module 3 in the morning, I'm going to post some answers for particular, for specific. Right, so using the formula from B1, what was B1? Oh, so for B1 it says, write the formula which relates the speed of light, the wavelength, and frequency. But that C is the symbol for speed of light, and it is the wavelength times the frequency. All right? So that's the equation that relates speed of light, frequency, and wavelength. All right. So now they're saying use the formula from B1, calculate the missing frequencies and wavelength in table 2. All right, so if we say that C is equal to lambda V, right? And we want the frequency, then the frequency you would divide by the wavelength. So it is the speed of light, it is the speed of light over the wavelength that will give you the frequency. The speed of light is 3 times 10 to the 8 by this wavelength 1 times, is that -5 or 5? Let's see what I did. -5, 1 times 10 to the -5. The answer that there was 3,000. You can check back the spectrum to see which one it matches up with. All right, and then for this one now, the same, if speed of light is wavelength, C is equal to, also then is, for the persons in the Zoom, is persons from my class. Right, so C is lambda times V. So now if you want lambda, you will by V. So this time, on the wavelength is C. And in terms of the answer, I got 3 times 10 to the 14. All right, so I didn't check for these, so I can just check and see which ones they match up with. All right. The first one is radio wave and then IR. So this is radio wave. This is infrared. Root, read.
So it's the other way around.
The other way around. All right.
Sir, what are we using to determine that it's the wavelength, right?
No, for the first one, for this one, well, you have the wavelength out here. Yeah. So say I have wavelength actually for the both of them. So in the first one, they gave you the wavelength, and in the third one, you have it here. But if with electromagnetic spectrum, it has wavelength and the frequency. You have the chart with you. Right, so this is the simple formula that you would use to calculate it. So just remember C is lambda times V, and you can always transfer. So let's go again. All right, so this is, so when a covalent molecule absorbs UV-Vis radiation, electrons are promoted. This phenomenon forms the basis for UV-Vis. So in UV-Vis, we have antibonding molecular orbitals, they have bonding molecular orbitals. They have sigma bonding and they have pi bonding molecular orbitals. These are where the electrons are located. And they can move up into the anti-bonding molecular orbital when they absorb UV light. You have sigma bonding molecular orbital, you can have the sigma anti-bonding, in which is just an asterisk. And you have pi bonding, so you will also have the pi anti-bonding molecular orbital. And then you have N, which is for non-bonding. All right. So electrons can move from bonding molecular orbital into the anti-bonding one, as well as from the non-bonding. Electrons will move from these and come up here. So I can start with non-bonding if I want. All right. And then I can go to pi. So they can go into any of the two antibonding ones. In total, it would be 6. And then from sigma to anti-pi and anti-sigma. So there are 6 transitions, 2 from each. So non-bonding to anti-pi, anti-sigma, pi to anti-pi, anti-sigma, and sigma to anti-pi, anti-sigma. All right, so those are the 6 of them. So I notice here, because there's 2 things to occur. These are all the possible ones, but not all of them are used for, not all of them are applicable to UV-Vis spectroscopy. So not all the possible transitions are applicable. Right, so list the transitions now which normally produce them. We have anti-pi, non-bonding, anti-sigma, and pi, anti-pi. So these are the transitions that will work in that region. In terms of calculation for UV-Vis, as you should know, is the Beer-Lambert's law. A is equal to ECL. All right, so the absorbance of an iron thiocyanate solution containing 0.005 moles iron per mil was reported as 0.4900 at 540 nanometer. So that's the absorbance reading. Using Beer-Lambert's law, A equal ECL, calculate the specific absorptivity, including units of iron thiocyanate. Assuming a 1 centiliter cuvette was used. And in terms of unit, the molar absorptivity normally has units mole minus 1 dmq cm negative 1. Now this is in moles per milliliter. So we're going to convert the milliliter into dmq. If this amount, so 0.005 mole is in 1 mil, right? We know that 1,000 milliliter is 1 dmq. We're going to figure out how much would be in 1,000 milliliter. They would just times this by 1,000, and you would end up with 5. All right, so A is equal to ECL. We're trying to find E, so we're going to divide both sides by CL. E is equal to A over CL. Absorbance is 0.49. The concentration is 5. And the path length was 1. It is 0.49 divided by 5. And I got, I guess, 0.49 divided by 5. 0.098. And the units, let me just put it below it. To get the dm cube in the unit, that is why I did the conversion here.
Sir,
Yeah,
absorptivity is more per dm cube and concentration is more per dm cube. What is E?
E,
Yeah.
the absorptivity,
So what is A?
absorbance. Up here, remember, yeah. So each sample will give an absorbance reading at a specific wavelength. So the absorptivity, so absorptivity is different from absorbance. Right? So
Sorry.
yes? Was that a question?
No, I was saying okay.
Oh, okay. Yes. So this is the calculation that you will do for UV in terms of with this formula. So sometimes you will get E, sometimes you will get the absorbance, the concentration, and the path length to calculate E. It's just a matter of transposing. Never see this formula? All right, let's scroll down. All right, some IR. All right, so all the written sections. So just to repeat all the little definitions and so forth. I'm just going to answer it. Just write answer and post it. All right, so pair all joints. All right, so for infrared spectroscopy, you must know to interpret these charts, all right? Now, this is not difficult. You're going to get the booklet, so you will have the, what we call the wave numbers, right? But even without the booklet, let me see if I have the, all right. This is what we are going to do. We'll be able to identify alcohol, carboxylic acid, ester, and the carbonyl group. C is concentration. All right, yeah, so back to this. You should be able to identify alcohol, carboxylic acid, ester, and the carbonyl group. Using these numbers, right? If you get a chart and you want to interpret it, for the left-hand side of the chart, that is what will help you to determine if you have carboxylic acid or an alcohol. When you get up to this end, right, look in the region of the 3,000 mark, if you see a peak, it should be of a reasonable width. So something of about this size, that indicates the OH group, all right? Now look at the width of this. It is very narrow, so it's not OH, all right? Those are CH or CC bonds, all right? So round about 3,000, you see a narrow peak that is not OOH, that is not a carboxylic either, all right? If you see a peak like this, that is kind of broad, that's an OH in a regular alcohol, all right? If you see a peak that is broad, something like, all right, if you see something like this, up at the 3,000 mark, that's the OH group, the OH in a carboxylic acid. Without even using the specific number. Once you get a graph and you see a very wide peak at the left-hand side, that's OH, but OH for a carboxylic. As you see this, you know it's a carboxylic acid. Now, if you do not see it, it's not a carboxylic acid. So this one is not a carboxylic acid, it's not an alcohol, because you don't get those peaks. This narrow peak, that's carbon to carbon and CH bonds. No OH is there. Scroll down a little. No OH. Just don't have any OH. This one, as you can see now, this is your OH peak. All right. I wanted one with an acid. It's not there. I will post one with a carboxylic acid in the morning. All right. So the question now, it says, all right. So I told you, you should be able to identify alcohol, carboxylic acid, ester. For the ester, C double bond O, single bond O, C, right? That's the ester. So for the ester, you should have a peak. When we say peak, right, it must come very far down. So this is a peak, this is a peak. These ones, they are not far down, so we don't use them. All right. Use the ones that are coming very far down. As I said, this one, we don't really need to use it because we already know that alcohol is not there, carboxylic acid is not there. This is too narrow. All right. The C double bond O, that will come somewhere like about 1600. And if you check 2000, 1900, 1800, 1700, if you see a narrow peak anywhere in the 15 to 1700 region, that is C double bond O. So your compound is in this group. All right. 3 key regions that you look for. Somewhere about 1700, something close to 1000. And then the alcohol group somewhere close to the 3000 mark. So you look to the left, start off in the middle and to the end. All right. So this peak indicates that we have C double bond O. All right. Notice we do not have any at 1000. We don't have any coming down at 1000 or even 1200. That peak is absent. Since it is absent, it means that we don't have any C single bond O. This one is for something close to 1000. This is something close to 1600, 1700. Right? So this one is there, but this is not there. That should tell you that you have a carbonyl group. All right? The question, you are trying to identify figures 3, 4, and 5 belongs to 3-methyl butanol. They are trying to identify an alcohol, heptanone, a ketone, and methyl pentanoate, and ester. So you are trying to find which one is the alcohol, which one is the ketone, and which one is the ester. Now remember, ester has C single bond O. And we said that clearly that peak is not there. So this cannot be an ester. There's no OH group, there's no C single bond O. That leaves you with carbonyl group, whether aldehyde or ketone. And in this instance, they gave you the name of a ketone. So that tells you that it is a ketone. All right? So this chart is not very difficult to interpret. All right? It's just 3 specific groups you are looking for. The 3000 to see if you have any OH. Close to 2000, if you have a peak there, C double bond O is present. If you don't have any at 1000, there's no C single bond O. So for this graph, I know it is a ketone because OH absent, C single bond O absent. C double bond O is present. All right. So that is how I know that this one, it would be heptanone. compound is known. All right. This one now. Remember, if it was a carboxylic acid, the peak, it would be much wider. It would look something just like this in red. All right. So this is an OH peak, but just in a regular alcohol, not a carboxylic acid. If it was carboxylic acid, it would be a wide peak like this one here in red. All right. Because it is not wide, it's a regular alcohol. Next, you do not see any peak coming down close to the 2000 mark, right? Which means that the C double bond O is absent. And now you have one coming down for the C single bond O. Remember now, alcohol, if you look at the alcohol, right, the C, O, and H. You still have a carbon to single bond oxygen. So this one, we don't really need it because once you see this, you know it's the OH group for an alcohol. All right, but you still can mention it. So you have a peak here for C single bond O, and you have the OH for the alcohol. So this one would have been the alcohol. All right. Let's look at this one now. So clearly, there's no OH group, because remember this peak, it is too narrow to be the OH group. No OH group is there. All right. Now, look at this peak, E double bond O. Look at the peak close to 1000, C single bond O. Which functional group is that? C double bond O, single bond O. That's your ester. All right. So justification, the peak at this would be, let me see, about 1750. So this peak corresponds to C double bond O. Oh, for justification, you're just telling the wave number and what it represents. So this is a ketone. Reason why it is a ketone, the peak here at, let me see, 1918. Right, so the peak at 1750, you have a peak at, or a band, if you want to say a band. So the band at 1750, it represents C double bond. And you also have one at, sorry, also have a band at 10, 11, 12. You put the wave number and the functional group it represents. Right? So that is how we justify. So because we have these two bonds here, and this one up here, it is insignificant because every compound is going to have carbon to carbon bonds. So it's the specific functional groups that are important. All right. So the only one that was left off is a carboxylic. All right. So I'm going to end it here. As in the morning, as I said, I'm not going to, maybe I do it, maybe I don't, because yeah, tired, but I will at least post the answers. All right. So I'm going for module 3. I'm only going to work and post questions for atmosphere, the contact process, atmosphere contact process, and four of them: atmosphere, contact process, aluminum, and pollution. I will post follow-up for topics. Right. For module 2, I'm going to post uses of IR, UV, or you prepare the samples. Right. So just look out, I will post, write the answers and post them. If you have the study guide, SWOT or you prepare samples. Any equation, once it has an equation, know the equation. All right? Know equation, the uses, impact on the atmosphere. Regardless of how the questions come, yeah. Are we still live? The internet had went. Are you hearing me? Not sure if you're hearing me. Right. I was using the Wi-Fi from my phone, but it did. So is the stream still on? I'm not even sure. I was just wrapping up anyways. Yes, right. My internet had went a while ago, but I was just wrapping up. Not sure even where I was. Right, but I'm going to post more, and so just look out on the channel for videos of answers. All right. And don't. Oh yes, I was going to say there for module 1, I work a lot of past paper for module 1, so you can check the channel. There are videos for back titration, gravimetry, and so forth. Don't look at back titration. If it comes just so, please study UV, IR, gravimetry, and uncertainty. Module 1, benzene and the rest of stuff except acidity of organic compounds. All right. I'm going to get some rest now, and we probably about 9 o'clock thereabout, I will start posting some again. All right. Don't try to study everything. At least study 2 modules, depending on how your preparation is point. All right. I'm going to end here, and all the best. So we'll meet again in the morning. I'm actually going to end it now. You're welcome. right, so good night, everybody.